right, so we're going to finish off our unit on sequences and series by looking at the infinite geometric series. Okay, so first of all series could be infinite, right, technically, but when we go to find the sum, we find the sum of a partial sum, right? So a sum of a certain specific number of terms. So what we're going to do here is we're going to see that there is a very specific series that you can actually find the infinite sum to. So let's take an example here of this series. We have 1/2 plus 1/4 plus 1/8 plus ... It's going to go on to infinity. And I'm going to end up using this formula to calculate out the sum. Maybe you've noticed this looks a little different than the one we just talked about that you've been using all along. And the only difference is that I rearranged these terms. In the other formula, it was r to the n minus 1 and r minus 1. Here I have it backwards. And it really doesn't matter. Either way is fine, because it's just a matter of factoring out a -1 on the top and bottom, which cancels out. So I'm going to use this for a specific reason, and I'll talk about that reason later. So first of all, if we look at this infinite series here, the first term is 1/2. And our common ratio, what we're doing each time, is we are multiplying by 1/2. So our common ratio is 1/2 as well. So what we're going to do here is we're going to find the partial sums for 5 terms and for 7 terms. And then we're going to analyze that, look at it, and kind of compare numbers and see what's going on. Okay, so plugging it in for the sum to 5 terms, we get 1/2 multiplied to 1 minus 1/2 raised to the 5th power over 1 minus 1/2. Work this out, we get, simplify it all down, we get 1 minus 1/32, okay, which really comes out to be 31 over 32, which is approximately 0.96875. Okay, we'll leave that alone for a minute. Let's go over to the sum for the 7 terms. So, looks kind of similar, only difference is this changed from 5 to 7. Work this out, we get 1 minus 1 over 128, which is really 127 over 128, which when you divide it, we get a decimal 0.9921875. Okay, so I've only done it for the first 5 and 7 terms, but you can see both of these are very close to 1. And you can actually see just by adding 2 extra terms, we went from 0.968 to 0.992, which is getting even closer. So you can only imagine if I took this out to 100 or 1,000 or 1,000,000 terms, this would be 0.9999999 all the way out, however far you want to go. And at some point you're going to want to say, well, isn't that just 1? I mean, it's pretty darn close to it anyway, right? So yeah, I mean, we could say that it's approaching 1. It's getting closer and closer to 1 as we get closer and closer to infinity. And so let's take a look at why that is. Okay. So first of all, we're going to find that whenever your common ratio, and we're talking about the absolute value of the common ratio, whenever that is less than 1, your r to the n, which is this part of your formula right here, becomes really, really small when n becomes really, really large. So looking at this, it's this number right here, 1/2 raised to the 5th, became 1 over 32. And then 1/2 raised to the 7 became 1 over 128. And you can see that from 1 over 32 to 1 over 128, it's definitely getting smaller and smaller. It's because this exponent being bigger and bigger is making that number down there much bigger. And so 1 divided by a bigger number is a smaller number, if that makes sense. Okay. So why do we not have to worry about this stuff and that? Well, 1 minus 1/2 is 1/2, and 1/2 cancels with 1/2, so that basically just goes away, right? So really what we're looking at is the fact that this number right here and right here is getting really, really small. In fact, what we can say is that this value, r to the n, is going to approach 0. It's going to get so small the bigger n gets that we're just going to essentially say that it gets to 0. So it approaches 0. Therefore, if this approaches 0, you are only left with 1 minus 0. So what you can say is it's 1 minus r to the n approaches 1. Okay, so 1 minus 0 is 1, so 1 minus r to the n is going to approach 1. So what this all boils down to is that in this formula, as n gets really big, this whole portion, I'll even highlight it for you, this whole portion right here goes away. It becomes 1. Okay, and so if that's the case, what you're left with is a sub 1 divided by 1 minus r. So the formula to find the sum of an infinite geometric series is simply that. You take the first term and you divide it by 1 minus r. So let's test this out. Let's look at this example that we had up here. A sub 1 is 1/2. Our common ratio is 1/2. Plugging that in, we have 1/2 over 1 minus 1/2. Well, that's 1. And didn't we say this looks like it's getting closer and closer to 1? And in fact, it does. It approaches 1. So when you're actually figuring out the sum of an infinite geometric series, we're actually not figuring out the exact sum. We're figuring out what it's going to approach and get as close to as it possibly can, which is called taking a limit of something. But you'll deal with that later in pre-calc. Okay, so let's see how we use this. You'll see it's so easy. We love using these formulas if we can. Okay, so we have this new infinite geometric series, 1 minus 1/3 plus 1/9 minus, so we're going back and forth, plus or minus. That means our common ratio is going to be negative. What is the common ratio? Well, you're going to take a negative 1/3 and divide it by 1, so it's just negative 1/3. Which is good because that's less than 1. Remember, absolute value has to be less than 1 in order for this to work. So we take the first term, divide it by 1 minus our common ratio. Work that all out. We get 1 over 4/3, which is the same as 3/4. So that means this whole series, if we took this out to an infinite number of terms, would eventually approach 3/4 as an answer. And that's what you're going to be doing. When they say find the sum of the infinite geometric series, that's what they're saying. Okay, pretty simple. I think you'll like this section.